All right, so this is 12.3. This is on derivatives and integrals of vector valued functions. So derivatives and integrals of vector value functions. So primarily we'll concern ourselves with derivatives, but we'll do integrals at the end just to sort of finish it off. And so first we'll say derivatives of vector value functions. Oops, let's say VVFs. So let me begin by giving a formal definition and then sort of an informal definition. So formally, let's say formal definition. So if you recall the definition of a derivative from calculus, let's say for some f of x, we can define, so this is back in Calc 1, so you could define the derivative at a point. There are a couple of different ways you can do this, but one way is the limit as h goes to 0 of f of x 0 plus h minus f of x 0 over h. So likewise, we can do this with vector valued functions. And when we do this, you'll see the reason why we mentioned 12.2 briefly. Right? So given some vector valued function, let's say capital F bar of t, we can do, so I'm basically going to emulate the definition above, just changing the appropriate letters. So capital F bar of t0, or prime of t0, is the limit as h goes to 0. The numerator will be f of t0, let me not make a mistake there, t0 plus h minus capital F of t0 over h. So notice that the numerator here is a vector valued function, because it's a vector valued function minus a vector valued function. We're dividing by a scalar. The result is therefore a vector valued function, and then we take the limit using 12.2, which ostensibly says that, you know, we take the limit of the component functions. So this is great, this is perfectly fine. This is the reason why I wanted to mention 12.2, but in practice we don't do it this way. So the practical definition is much easier. So the practical definition is simply you take the derivatives of the individual functions, or the components if you like. So for a vector valued function, capital F of t, we calculate capital F prime of t by taking the derivatives of the components. So don't worry right now about what this means or what this represents or anything like that. Just look at an example, a couple of examples, like if f bar of t is t squared I plus, say, sine of 2tj plus e to the 3tk. And we can take the derivative, just take the individual derivatives. So 2ti plus 2 cosine of 2t, there's the chain rule there. J, chain rule again for the next one. 3e to the 3tk. You can take it at a point. Again, don't worry about it, what it means. If I plug in, say, 0, you get 0i, cosine of 0 is 1, so you get 2j, e to the 0 is 1, so 3k. And so on. And that's it, right? That's it for taking the derivatives. Again, well, also we could take second derivatives, third derivatives, so we can go further. The furthest that we'll go will be second derivatives. So like, for example, in the same example, the one above, could take the second derivative. Take another derivative, I get 2i minus 4 sine 2t j plus 9e to the 3tk, and so on. We won't go any further than the second derivative. So that's the practical definition. The thing that we're really interested in is what's this good for us. So that's what we'll focus on next. So let me clear the screen. Take a second if you want to digest this, right? Forget the formal definition. It's interesting, but you don't need it. The practical definition is take the derivatives of the components. So what we'll do next was look at some ideas behind like what this thing can mean for us in this course. So C. I'll say, well, we can say application or use, if you like. So what I want to do is remind us of what we're using vector valued functions for to begin with, right? So there are a variety of things, but we have a primary use to focus on. So recall that we mostly, I'll say saw because it's past tense, saw vector valued functions as a way to represent the motion of objects. Really the location. Let's say the location of objects at a time t. So for example, if we had something like r of t, say was ti plus t squared j, then we think, let's say at time t, the object is at x equals t, that's the I component, and y equals t squared. So you can plug in various times, find specific locations, you can plot like a path that the object takes and so on. But this is what we think about when we think of a vector valued function. Right? So using this sort of understanding, what does the derivative get us? So let's say, what does the derivative do for us? So what I'll do is I'll just sort of run through there are three things that are going to emerge. Then what we'll do is we'll do an example and we'll sort of see how these things look visually just so we believe it. We'll do a couple of examples. Right? So this is what happens, right? So given, let's say location r of t, we have the following, right? So first thing, the first derivative, this gives the velocity. Now keep in mind this is a vector. So velocity vector of the object. It points in the direction of motion, as we'll see. This is often denoted v of t, and its length is the speed. So I'll say its length is the ... because that's the next definition. So the length of a vector is the absolute value. So the absolute value of r prime gives the speed. This is scalar. This is often denoted, up here I wrote oft, this should be often denoted s of t, not a vector, because that's a scalar. Then if we go one step further, we have second derivative. This is the acceleration. This is acceleration of the object. This is sometimes a little harder to visualize. It's sort of like visually it gives you both an idea of how the direction is changing and how the speed is changing. So this sort of encapsulates, if you like, how both direction and speed change. So before we do an example, I'll just put a little note here, and then we can clear the screen and do an example, is so that these two vectors, actually, so the one last thing I'll put in here for the acceleration, this is often denoted A of t, A bar of t, also a vector. So the note I want to make is that v of t, so something we learned about vectors is they can be anchored anywhere. So the velocity and the acceleration, those are anchored at the object because we think of them as properties of the object. We'll see what this looks like when we draw a picture. This is because we think of them as properties. So let me clear the screen so we can sort of see it all together, and we'll work through an example. So again, the things to keep in your mind is the derivative is the velocity, the magnitude of the derivative is the speed, the second derivative of the position is the acceleration. Acceleration and velocity are both vectors. Those are anchored at the object itself. Let me clear the screen out, and then we can go through a couple of different examples so we can see how this looks. So here's first example. Let's say, and we'll do examples just in 2 dimensions because it's significantly easier to draw if we don't have software available. So let's do ti plus t squared j. Now just for the record, we're going to focus at the point t equals 2. But just for the record, we know what this looks like. This was a graph. If we didn't look at it, we looked at things that were very similar. This is the graph of a parabola. Because in this case, right here, x is the t value, or the I component, and y is the j component. So put those together, we get y is x squared. So this thing is following a graph like this. This is the motion of the object in the xy plane. Now we'll draw a better picture in a second. This is so you have something in your head. So we're going to focus at t equals 2 up here. So the location. This is at r of 2. This is 2i plus 4j. So we think of that as a position, 2, 4. The velocity, we find the formula for velocity, r prime. This is 1i plus 2tj. We look at t equals 2, because that's where we're focusing. Get 1i plus 4j. Leave that alone for now. The speed is the magnitude of that. So square root of 17, 4 point something. The acceleration is the second derivative. This is 0i plus 2j. I'll plug in the point. There's no t's left, but it's worth plugging it in just to sort of cognitively be aware of what we're doing. That's the acceleration. So if we draw this together, and I want to draw a reasonably accurate picture, so like our y scale will need to go up to 8, as we'll see why in a second. So we'll divide that up nicely into 8. So the x won't need to go so far, but I want to keep the same ratio so we believe the various slopes and vectors and so on. So location of the object is at 2, 4. So that is right about there. That's traveling along our parabola. We can draw the parabola in, it won't hurt. That's the way it's going. Should be curving a bit more. Let me do a slightly better job. That's motion. That's the actual route it's taking. The velocity, that's the r prime of 2. That's this guy right here. That's 1 unit over and 4 units up. So the location of the object is at 2, 4. So if we go 1 over and 4 up, we were at 3, 8. It's right there. So this is the vector right there, v of 2, or if you prefer, r prime of 2, 1i plus 4j. And that makes sense. If the object is traveling in this curve at that point, that's the direction it's heading. Now the speed of that is the square root of 17, that's the length. So the length is the square root of 17. I don't have to think about that when I plot it. That just comes out because of the vector being 1i plus 4j. And then last but not least, the acceleration right here, down there, that's straight up 2 units. That is our a of 2, or if you prefer, r double prime of 2, 0i plus 2j. And that's sort of pointing left of the green arrow because the green arrow is sort of turning as the object goes up. So that captures everything about sort of the motion of the object, the position, well, and the first two derivatives, the position, the velocity, the speed. Let me actually sort of make sure that we're clear. This right here, that is the speed. And the acceleration. So take a second to digest that, and we'll do one more example. Very different graph. The second example, something like r of t equals, let's say, 1 plus 2 cosine t I plus a 3 plus 2 sine t j. And we're going to, let's say, look at t equals pi over 2. This will be pretty nice. Now this one we also know. This is a circle. It's offset, so it's centered at 1, 3, right there, as a radius of 2. So it looks something like this. When t equals 0, it's over here, and it goes counterclockwise. So again, let's run down the line. Let's say location. You could probably guess where it's at. You could probably guess just from the picture. So cosine of pi over 2 is 0, so I get 1i. Sine of pi over 2 is 1, so I get 3 plus 2 is 5. That is at the very top. That is 1, 5. The velocity. Take the derivative. Derivative of cosine is negative sine. Derivative of sine is cosine, so we get 2 cosine t. Plug in the point. Sine of pi over 2 is 1, so I get negative 2i and 0j. The speed, so the magnitude of that. So the square root of 4 is 2. Nice and easy. And the acceleration, take the second derivative. Negative 2 cosine ti minus 2 sine tj. Plug in. Get 0i minus 2j. So again, let me try and draw a reasonable picture. Although this one we could be a bit sloppy with, we won't. We'll try not to be. We could be a bit sloppy because the vectors are all particularly nice. So the object is at 1, 5, so that's right here. So this makes sense because the center of the circle is right at 0, 3, and it's a circle of radius 2. So the object is sort of going this way. It's going to the right. Or to the right on the bottom, to the left on the top. So this is where it is at t equals pi over 2. So velocity in this case is directly to the left, which makes sense because it's sort of heading, that's the direction of motion. That's v of pi over 2, or r prime if you like. And then last but not least, the acceleration is straight down. And that's it. Nice simple example. So that pretty much tells us what derivatives are good for. But in closing, let me make one final comment about derivatives before we go on to integrals. So let me clear the screen off, put that next, and then we'll go on to integration. So D, properties. So this is really, really brief, and these will be sort of very commonsensical. I just want to mention them to sort of embed them in your head, so when we see them later on, you won't be overly surprised. But all I really want to say here is that derivatives of vector-valued functions act like derivatives. Now, if it's not clear what I mean by that, that's okay. I'll just list a few things. So, first thing, if you add two vector-valued functions and take the derivative, that's the same as taking the derivative of the sum. Should be no big surprise there. Same with subtraction. The things that are interesting is if you have like a dot product. Right, so one thing we said about the dot product, that you can dot product two vector-valued functions because they're vectors. One thing we said about the dot product is it's called the dot product because it acts like a product. So, take a derivative of product, you should get the product rule. And so, lo and behold, you do. Acts just like you think it does. This isn't obvious because these definitions are tricky, right? The dot product is not an obvious definition. Same with the cross product. You get like a product rule. You get the product rule. So these are not typically used in practice. They crop up in some theorems here and there. So don't worry about memorizing them. Just sort of tell yourself in your head like, hey, derivatives of vector-valued functions act like you expect derivatives to act, and everything's fine. And leave it at that. And I'll leave it at that. We'll do examples. We'll see that come up. So then the final thing, second part, is integrals of vector-valued functions. So I'm going to mention both definite and indefinite integrals really briefly. Definite integrals we won't really use. I just want to mention them because it's a good beginning before we mention indefinite integrals. So definite integrals, remember, have limits of integration. These do mean something, but they won't be used, like we won't be using them. So that's why I don't want to spend too much time on them. So we'll say when doing a definite integral, all we do is integrate the individual functions. Well, let's say the individual components. So for example, if we were to do something like the integral from 0 to 1 of, say, ti plus 3j plus 2e to the tk, all you do is you integrate them independently. So 1/2 t squared I plus 3tj plus 2e to the tk, 0 to 1, plug in 1, I get 1/2 I plus 3j plus 2e to the k, plug in 0, get 0i plus 0j plus 2k. Then that can be simplified, but I'm not going to worry about that. Right? But basically, that's just the process. You just blast through it, you integrate the individual components, call it a day. Now, the same is basically true for indefinite integrals. So you might wonder why we're mentioning them. So the reason is twofold. One is there's a quirk that comes up with the constants, and the second thing is because we'll need them for a specific type of example. That's what I want to mention. I want to do one of those examples. So we'll say similarly, here we just do the components. But dot dot dot. So let's look at an example. All right, so if we had, say, the integral of 2i plus t, let's say 2tj plus e to the 3tk. So you might say like, okay, well, all I'm going to do is integrate them independently. Right, so when you integrate 2, now it's an indefinite integral. So you integrate 2 and you get 2t plus ci, because you've got to have your plus c for an indefinite integral. And then you've got your t squared plus c. Some of you might see a problem already, and that's great. And then you get 1/3 e to the 3t plus c. Okay. So what might worry you, of course, is that these c's don't have to be the same. These could be different constants. So these c's might be different. So using c for all of them is bad, because you might run into a problem like that. You might get a value for one and think it's the same value. So you might say, well, okay, so if that's not good, let me just use different letters. Or I could do like, say, C1, and then C2, and then C3. Now, this is not wrong, but it's icky. It's an unhappy face, right? The reason is that you've got like 3 different things that you have to carry around now that you don't know, so it's a bit awkward. So better would be something like the following. Forget the constants for a second. And then at the end, add a constant vector. What that constant vector is doing is it's sort of scooping up everything. This represents plus C1i plus C2j plus C3k all together. Like without writing them separately, it represents everything. This makes things much easier to work with than lugging around 3 different constants all the time. So let me end this by doing an example of how these indefinite integrals are useful related to the work we just did with the motion of an object. And then as we work through that, you'll see why the c, having a c with a bar over it, is much more convenient. So let me clear the screen off and do an example to end on. So for example, now the example I'm going to do, you've actually done examples like this in calculus with regular functions of one variable. And so the idea is this. What we're going to do is we're going to suppose that we know the acceleration of an object always. So maybe the acceleration is always, say, 2ti plus 0j plus 2k. Suppose you know the velocity, but only at a point, like 0. Maybe that's 2i plus 1j plus 3k. And then suppose you also know the position, but only at an instant, like maybe at 1. Say 10i plus 10j plus 0k's. So what we're going to do is we're going to find the position always. And so what we do to do this is we start from the acceleration and we work our way backwards, right? So in other words, we're going to say given the acceleration. Right, we know that the velocity is the integral of acceleration because the acceleration is the derivative of the velocity. So this is the integral of this 2ti plus 0j plus 2k dt. So if we integrate this, now the integral of 0 is kind of technically a constant, but that's going to be taken care of by our plus c bar. So that c bar takes care of it. Right? Now, this says that v of t is all this stuff plus c, but we need to know what the c is, right? In order to actually have v of t, we need to know, like, what is this? So you go, well, let's see. Like, we know v of 0 up at the top. and I can find v of 0 using this. So in other words, v of 0 from this v of t right here is 0i plus 0j plus 0k plus c bar. That's coming from right, let me label that, that's coming right from there. But I also know it from here. Right, I know that v of 0 is 2i plus 1j plus 3k. So this is an equation that lets me solve for c. Right? Now, in this particular case, it's really nice because there's nothing but zeros on the left. So it actually just explicitly tells me what c is. Then I can take the c, and I can plug this c back into here to get a final version of v. So v of t is t squared I plus 0j plus 2tk plus this thing we just calculated. That's our c bar, which we can combine to make it pretty, put it all together. T squared plus 2i plus 1j plus 2t plus 3k. So what we've done is we've got from a of t to v of t, and now you can probably see like what are we going to do? We do the same thing again, right? So now we go, well, r of t is the integral of v of t. We just did v of t, that's our t squared plus 2i plus 1j. These problems take a little while to chug through, but they're good derivative and integration practice, which we'll be doing a lot more of in the course. So we integrate that, we get 1/3 t cubed plus 2ti. Remember the constants are all going to come at the end. tj, t squared plus 3tk. Now I'm going to use a different letter so I don't confuse myself and think it's the same c, because it isn't. But again, we now have a d here. We need to know what it is. So just like before, we say like, well, this is our r of t. Now in this case it's r of 1 that we know. So r of 1 here is 1/3 plus 2i plus 1j plus 4k plus d bar. That comes, I'm using a different color, that comes from here. But it can also come from here. The data that was given. So this is 10i plus 10j plus no k's. So now we can solve for d. It's a bit icky, that's okay. Hopefully I won't make any mistakes. So on the left we have 2 1/3, that's 7/3 I. On the right we have 30/3, so subtract those, we get 27/3 I. 10j minus 1i is 9j. 0k minus 4k is minus 4k. Also just realize that should be 27/3 right there at the beginning. That was 30/3 minus 7/3 is 23/3. That's our d. So then we know r of t. That again is going to get plugged. That guy will get plugged. Oops, let me use the right color. Just trying to be consistent with the colors here. Now we'll get plugged right back into there. And then tidied up. So we get 1/3 t cubed plus 2ti plus tj plus t squared plus 3tk plus this d that we just found. So put all these together. I get 1/3 t cubed plus 2t plus 23/3. That's the I. T plus 9j. And t squared plus 3t minus 4k. So, you know, again, not a difficult problem, not an exceptionally thrilling problem, but an interesting use of integrals related to derivatives, vector valued functions, physical real world situation, etc. So that's the end of 12.3, and that is done.